Greetings. This is Graham Warren. So the first kind of analysis that I'd like to sort of sketch out for you is, how to use the queuing calculator to explore some of these scenarios. So, in pretty much all of the analysis that you would do, either in a case like this or, in practice would be to evaluate the base case, the current scenario, assuming that you have an existing operation. And the key here is that we have unpooled orders coming in at the rate of 18 per hour to each of these Venus Arduinos. And these baristas are able to, produce caffeinated beverages at the rate of 35 per hour. And we can use the GGK calculator to assess things like the utilization of the barista and the waiting time in the system. I'm taking the waiting time in the system as, the primary KPI here because, that's what the customer really experiences, right? They come in, they place an order. So, how long is it from time of order to cup in hand? I think most folks are going to agree that, that's a useful measure and something that really matters to customers. So the time in system is going to be composed of two things: the actual time to make their order, as well as the waiting time before the order starts. So that together is the time in system. If you're only interested in the time in the queue, then we can figure that as well. You'll see that in the calculator. Right. So we're going to be evaluating the current operation, which has untrained baristas who are providing service with a mean service time of 103 seconds, standard deviation of 60 seconds. Arrivals are at the rate of 18 per hour. This 103 is roughly 3,600 seconds in the hour divided by 35. That's how we get the 103. And then, we can explore different things like, what if we train? What if we pool the orders? What if we switch from the Venus Arduinos to the Juras, the automated machines, and maybe some blend of, all of these proposals. In addition to that, there, could be other sort of experience enriching proposals that you may look to come up with. But let's at least see if we can get through some of these basics in this clip. All right, so I want to not do that. I want to pivot here. Now, this GGK calculator is linked in the analysis, in the canvas and also in the case. And I want to lay out for you how we're going to analyze this first one. So each of the three Venus Arduinos has essentially an identical barista. So we only need to analyze just one barista Venus Arduino since they're independent. So they see arrivals at the rate of 18 per hour. So we've got, what is really an MG1 queue here. I just annotate this. Okay, so we've got arrivals. Let's try that in maybe white on this background. So they're coming in at the rate of 18 per hour. They're waiting. Here's the waiting line. And then they're getting service at the rate of 35 per hour. But, the richer account here is that there's a normal distribution with a mean of 103 seconds and a standard deviation of 60 seconds because they are untrained. And after that beverage is made, they get it, they drink it. But from the perspective of our analysis, we're done. So the squared coefficient of variation of a Poisson process is 1. What is this statistic? It's basically your standard deviation divided by your mean. So we are going to have to calculate this for the service process, and I'll show you that now. So right now I'm going to analyze a one service system because each of those three Venus Arduinos is identical. And this calculation for this thing, I'm just going to write out the formula for you. So CV, it's a P squared, is going to be the standard deviation divided by the mean. And you square this thing. So in our case, standard deviation is 60. The mean is 103. Square this. I'll plug that in. And I get looks to be 0.3393. Okay, so I'll just plug that in. And we say submit. And here is your analysis. So I'm looking at two key quantities here. First is the utilization. So in the base case, each of these baristas is going to be working a little bit more than half the day, 51.43% of the day. Seems a bit low, but just something to note. And then you can certainly get the waiting time in the line. You can also see how many people are on average in waiting in the line. But the key quantity here for me is this guy here, the time in the system. So that is expressed in hours. 0.0488 times 60 is 2.928 minutes. So this is hours. Just click away from that, equals 2.928 minutes. So, this is something you may look to tabulate to document what's going on, but that's the initial look. So I'll get rid of this now. So the base case then is, let me just back out of here so we can just get a full picture. The base case, we've got a waiting time on average of 2.928 minutes. Now, one thing to bear in mind is that this is just the average. We don't know what sort of the worst case is, and you may look to come up with a proposal that does restrict the worst case. Maybe not too many folks are going to care about a 3-minute turnaround, but if the worst case in that average of 3 minutes is 16 minutes, that's a different matter. So let's now explore what happens if we train. So if we train, what happens is this 60 minutes becomes 40 minutes. So I'll just put it below here. So this is sort of basic training. And if I go with the advanced training, then it's going to be 40 divided by 103 squared. And what I get then is 0.1508. Okay, plug that in. And I'm going to say submit. Now you can see that the utilization did not change. Interestingly, utilization depends only on the arrival rate, the service rate, and the number of servers, not on variance consideration. So the utilization stayed the same. We've still got 3 separate independent baristas, but now they're trained. And so because of the training, the variance came down on their service times from 60 down to 40 seconds. And what this does is it reduces the average time in system from 2.928 minutes to 2.76 minutes. So this is the basic training, W sub S, and here is the advanced training, and 2.76 minutes. Right. So it's not the only upside. I mean, the quality of the art is better. They're really high-end baristas now after this training. Let's explore another possibility. I want to go back and explore these changes one at a time in a marginal fashion for you. So I'm going to just erase all of this. Just make a note of these p-values. Okay, so delete these. Now I want to explore. Well, actually, let's have a look at one more. Let's say we're in the base case, and instead of training the baristas, we just bring in the new machines, the Juras. So I think what we're going to get then is CV sub p squared is going to be 5 over 103, and we square that. So 0.0023, if I have that correct. Yeah, needs to be correct. All right. Everything else remains the same because all we're doing now is going from the base case to the Juras. We're switching out the machines. 2, 3, let's say 6. Utilization remains the same because again, it's just changing the variance. And now I'm at 0.0437. So 2.622 minutes. So write that in. So that would be hours, and that would be 2.622 minutes. So definitely you're getting improvements. That's for you to decide, if these are something you want to pursue. Want to look at another change now, and that is where I go back to the base case. So my base case had a CV sub p of 0.3393. What I want to do now is I want to pool the orders. Instead of having them being randomly assigned to one of the order queues for each barista, I'm going to have just a central order queue, and then have those 3 baristas all pull from it. So they're in parallel now, essentially. So if I lump these orders together, each of these streams coming in there is 8, the folks are coming in there at the rate of 18 per hour. So now if I lump all these together, it should be 18 times 3 per hour. So that's 54 per hour. And now instead of having a single barista, I've got, K equal to 3. And that's how I'm analyzing moving from the base case to the pooled order system. So it's 54 on the arrival process, and I've got 3 down here. The service time distribution remains the same. These are now 3 basically trained baristas. And here is my result. So now you'll notice that again, I'm still at 51% utilization. And my time in system is 0.0325 times 60 is 1.95 minutes. So this is a relatively easy thing. So that's in hours, 1.95 minutes. Now we could, just look at one change in isolation. Certainly that from an operational, change perspective, that may be easiest to implement. Of the changes entailed here, I think the Juras are about the same cost as the barista training, so that's about a wash, right? So the cheapest option here would be to pool these orders. Presumably that's just a tweak in that Emojot software. And the other 2, come with a cost, but there's pros and cons associated with these that you're going to have to pick through. So the next question would be, okay, so what about doing a mixture of these different machines? What about having like one Arduino just so everybody can see what it looks like, and maybe 2 Juras? Certainly a possibility, and you could analyze those cases separately. We just did. We saw what if you're just running a Venus Arduino for a barista, what performance looks like and what the performance is for a Jura, and then you could average out those results to figure out what a mixture of the machines may look like. I'd also like to give you some kind of a composite scenario here. So one thing we haven't explored is reducing the number of baristas, and that's something you could easily do by just going in here and changing K from 3 to whatever other number. Maybe you need more baristas for you to decide. But let's have a look at one sort of composite scenario. And what I'm going to do is I'm going to look at what happens if we were to get the advanced barista training and to pool the orders. So to get that to go, all I need to do, so I've currently got it set up for the pooled scenario because I've put all the orders together. There's 54 coming at 54 per hour coming in at that pooled order queue. 3 baristas are serving it. And instead of using the CV sub p squared for the basic training, I'm just going to switch that out to the advanced training, and I'll run this. All right, so now you can see I'm still at 51% utilization. And now my time in system is 0.0319 times 60. So now it's 1.914 minutes. So this is hours, 1.914 minutes. Okay, now last look would be to maybe look at what happens if we take the base case, we implement pooling, we train the baristas, but we fire one of them, let's say. How's that going to look? Okay, so notice here, I'll clear the information. Notice here that I'm no longer at 51%, I'm now at 77%. So the baristas are working. Now there's 2 of them. They're sharing the third barista's work, who's, now, on a new career path, let's say. And what's the time in system? So I see 0.0533. So this here is 3.198 minutes. So there's a possibility, but other possibilities, you have to make a decision on the training, you have to make a decision on the machines, and on the pooling, and then come up with a composite scenario. So that, in a nutshell, is how we could analyze Antico Cafe Greco into some of the scenarios, in pursuit of a recommendation for these folks.